So now that we've talked about how to measure the center value of a given population or sample, let's talk about another property. And this property is a measure of the variation of a population or a sample about the center. And this is section 1.5.3. Okay, so if we defined delta x sub I as the difference of the ith value from the center value, in this case we'll use the mean, one way of sort of characterizing the variation of the sample would be to take the average of that delta x. And what would that give? Well, if we take the sum of xi minus the mean value divided by n, then we get the sum of xi and we're summing x bar n times, so we get n x bar over n. And what does that give us? Do you see it yet? So that gives us x bar minus x bar, and that's equal to 0. So that's not a very useful measure of the average average variation. But oftentimes we don't care whether each value is less than or greater than x bar. We really care about sort of its absolute deviation from the center value. So the absolute value of x, delta xi. So therefore we could take the average or the mean absolute deviation. And Russell refers to that as AD, and that's 1 over n of the absolute value of delta xi. And that will be, in general, non-zero. Now, a more common way to measure the variation within a sample or a population is referred to as the variance, or the square root of the variance is the standard deviation. And for the population, the variance is denoted sigma squared, and that's defined as basically the mean square deviation. Oops. We're talking about the population, so we're looking at the deviation from the mean of the population, which is mu, and that's squared. And then for a sample, the variance is s squared, and that's just the mean deviation, squared deviation in the sample. And one thing I need to correct for is we don't divide by n, we divide by n minus 1, because n minus 1 for the sample is the number of degrees of freedom, which is the number of quantities that goes into calculating S that can change freely. They're not dependent on each other. And a definition of a degree of freedom for statistics, for calculating statistics, is the number of observations, which in this case is little n, minus the number of statistics used to estimate a parameter. And in this case, the parameter we're estimating is sigma, and sigma squared, and we're estimating it with the sample variance, little s. So in this example, we have n observations, but we're using the mean of the sample, which is one statistic, and we're using that one statistic to estimate the population variance. So we have to subtract 1 from n to get the number of degrees of freedom. So the standard deviations are sigma, and that's just the square root of the variance of the population, and s, and likewise that's the square root of the variance. So now clearly the variance of the sample, or the standard deviation, depends on the central location that or the value of x that we choose as the central location. So let's look at variance again. And instead of x bar, I'm going to write a general value xc, where xc is our chosen center. It's the quantity we choose to describe the center of the sample or the population. So let's ask the question, what xc minimizes s squared? So what central value should we choose if we want to minimize s squared? Okay, and so how do we calculate that? Well, and Wessel does this on page 29, but we could take the derivative of s squared with respect to xc, the central value, and set that equal to 0, and solve for xc, because a minimum will occur when there's no slope in this function right here. And you can work through Wessel's notes to do that, but what you find is that xc is equal to 1 over n times the sum of all the points in the sample. And that's equal to x bar, the mean m. So the mean gives the least square estimate of the central location. Or the L2 estimate for short. That's the location that minimizes the square deviation. So now let's ask the question, what is XC that minimizes the mean absolute deviation? Okay, so remember the mean absolute deviation is equal to 1 over n times the sum from I equals 1 to n of the absolute deviation of each value from the center value. And let's take the derivative of AD with respect to XC. And when we do that, we get a minus 1 over n times the sum of xi all over xi minus xc. And we got to set that equal to 0. And what you'll notice is that for x less than xc, dAd dxc is equal to minus 1. Okay, for x greater than, oops, see if I can write what I'm trying to write here, xc. For x greater than xc, the derivative is equal to positive 1, right? So we want to find the value of xc that gives a 0 if we sum everything. So we want xc for which half of the values give a minus 1 and half of the values give a positive 1. And that value of xc is equal to the median. So the median minimizes the absolute deviation AD and is an L1 measure of the center.